Okay, everyone, welcome to AP Physics 1, test cram video number 1. Just be talking mostly concepts now, and these videos may not be quite as organized as other videos I've shown you, but this is just to talk concepts, so let's get started. First video is about projectile motion and free fall. So we have a dilemma here. A baseball on the left side here just drops straight downwards. The other one on the right is tossed upwards first, and then it comes back down. Okay, first dilemma is what acceleration do both of them have? Of course, not. They're only under the force of gravity. We're going to ignore air resistance. So the answer is they're under the same acceleration. Acceleration for both will be negative 9.8 meters per second squared. Often the concept is since this ball is going upwards, you're thinking that there's some kind of positive acceleration right now. But we're taking it from the perspective of both of these balls have been launched. This one simply dropped. This one is now going upwards. So they're both under gravity going straight downwards here. Of course, this one here will just go straight down. It'll reach the ground in some time t, and you will use what I call the Fab 5, your displacement equations that you've learned in Chapter 2 of physics. Okay, this one here, though, is going to go up. It's going to reach a max height. Okay, and remember that velocity at that point is going to equal 0 meters per second at the maximum height. It'll then reach that max height. Let's say it's up here somewhere. Then it's going to fall back down, and eventually, okay, it'll reach the ground at some time. But what about when it's located here? So let's say we give it some kind of velocity here, a positive velocity here, and let's call that v naught. Okay, when it reaches max height, of course, it'll be 0. Ignoring any air resistance, when the ball reaches here, it'll now be traveling downwards, and let's call that negative v naught. So when it returns to the same height from whence it was launched, it'll now be a negative value of that initial velocity going upwards. Okay, and then it'll just continue to come down, and let's just say it'll have a negative v2 value when it hits the ground here. And of course, this one here, initial velocity is going to equal 0 meters per second, and then it too will hit the ground at a negative v2. But it's important to note that the velocity here that it hits the ground will not be the same as the velocity when it's launched vertically upwards. Okay, and the time it takes, of course, for the one that goes up and down is going to be much larger than the one that's just dropped. So again, just, don't get confused. The acceleration for both is all just due to gravity going straight downwards. Don't get confused that this one's going upwards. The fact that the velocity vector initially is going upwards does not affect the idea that there's an acceleration going downwards. Just think force. Both of these things are under free fall, and the only force involved, of course, is the force of gravity. Now, what if we change things here? We have a ball here that is just dropped again, going straight downwards. But we launched this one, okay, as a horizontal projectile. Let's give it a v naught initially here. Okay, and again, do not get confused. They're both launched from the same height. The time it takes for this ball to reach to the ground here is going to equal the time it takes this ball to reach the ground. Okay, because in the x direction is the beginning velocity. There's no velocity given in the y direction here. So they're both under just free fall. Again, force of gravity here, ignoring any air resistance. So they're coming from the same height. In the y direction, there is no difference. The fact that we're going to the x direction while we're falling does not change the time of fall. But this one, of course, will do some kind of a parabolic arc. It'll eventually, reach the ground. Okay, at the same time that this one reaches the ground, but it will be some distance in the x direction away because it has this velocity in the x direction. Okay, when I teach the subject, I tell my students the x direction really has nothing to do with y, okay, but they are bound by time. The time it takes for it to freely fall downwards is going to be the same for both of these guys. The only difference is the velocity vector for this one, when it hits the ground, let's just say this is a v2, it will be a straight down velocity vector. Okay, when this one hits the ground, though, it's going to hit the ground at an angle. Okay, and let's represent that just using an arrow downwards like this. Okay, and a reminder then, there will be a velocity in the x direction, okay, and a velocity in the y direction. Okay, and the velocity in the x direction is still going to be that v naught. There should be no change if we're ignoring air resistance on the way down. Okay, and then we'll have a v2 in the y direction, and that'll need to be to get the velocity resultant of that. You'll need to Pythagorize the v naught, which was in your x direction, and the v2 in the y direction. And again, you'll get that using what I call the Fab 5, your simple equations from chapter 2. You can even do like a v2 squared equation or something like that. But then just do Pythagorization and inverse tangentization to get the velocity vector. And one more topic to cover. What if instead of launching this thing at a horizontal, we do launch it at some kind of an angle? Now we're going to see a difference. The time it takes for this to fall is not going to be the same as this right here. And there's a good reason for that. Let's trace this velocity vector up here just a little bit more. Okay, and I'll make that larger so we launch in that direction there. There will be an x direction, but there's also a y component. Okay, if we call this a v naught, now I will have a v naught in the y direction and a v naught in the x direction. So the ball will go up some. We have affected the y, and the time it takes for it to simply fall downwards will not equal this. It's similar to our first question that we looked at. So there will be a parabolic arc that goes up. Okay, and let's see if we can kind of sketch that in there. It'll go up like this, reach some kind of a maximum height, okay, and then come down to the ground below. So one more time, we'll have a velocity vector that's got an x component and a y component to it. And but this one will only have a y component. Let's talk about at this maximum height, though. Our velocity vector at that point is just going to be in this direction here at max height. Let's investigate y. Well, at max height, velocity in the y still equals 0. So at this point, we just have a v not in the x direction. Okay, because we're at the max height, vy is still 0. And the range of this projectile is going to depend, okay, on the value of v naught here and the angle here. And of course, when this lands, let's just draw a quick, diagram of that. When this lands, it will be at an angle. And if we break this up into x and y components like we did before, we will have in the x direction of v naught x, but in the y we'll have a v2 in the y, and again getting this angle here, Pythagorization and inverse tangentization. Now for any given v naught, our maximum range again for the projectile, if we're not including the beginning height, of course, beginning height's going to affect things, but our maximum range really is going to be the angle 45 degrees. So your 45-degree angle launch will give you your best horizontal range. The distance it takes, or the ball moves while it's in the air in the x direction is called the range for the object. Okay, and that does it for our first video. And our next video, of course, will be going into more things to help you cram for the AP Physics 1 test.